As we saw in the previous video, partial fractions spits out four possible terms, four possibilities for what your denominators will look like when you are trying to integrate a rational function. So to integrate a rational function, all we need to be able to do is figure out how to integrate those possibilities. So let's start at the top. The first one looked like this, 1 over x minus c dx. And you might be able to just guess this antiderivative. In fact, let's just guess. You might expect, well, look, there's a 1 over x type thing, so probably there's a natural log. Probably it's natural log x plus c. You need plus a integration constant, of course. And if you check this derivative, it does indeed work. The derivative of natural log x minus c is 1 over x minus c times 1 from the chain rule. And so 1 over x minus c, we know how to integrate that. All right, so let's move on to the second possibility. This was if you had a linear denominator to a higher power, like this. And for this situation, well, now it kind of looks like the sort of thing that we want to use a substitution for. So if we do a U-substitution, we should let u be x minus c. Then du is just dx, which is nice. So this integral turns into integral 1 over u to the n times dx, but dx is equal to du. And then we can use the power rule to calculate this antiderivative. We get minus 1 over u to the n minus n minus 1, yes. And we need an n minus 1 in the denominator here, plus a constant of integration. Okay. There's a 1 hiding in here. There it is. And you can check that this derivative, the derivative of this, is 1 over u to the n. Okay. Of course, we should probably undo our substitution, so we get minus 1 over n minus 1 times x minus c to the n minus 1 plus a constant. Okay, so that's the second possibility down. 2 more to go. The third possibility was an irreducible quadratic, and sort of my own personal archetypical irreducible quadratic is x squared plus 1. So let's integrate 1 over x squared plus 1 dx. And this particular irreducible quadratic, something very nice happens. This is actually the derivative of a function that we've seen, arctangent. So the antiderivative of 1 over x squared plus 1 is just inverse tangent of x plus a constant. Okay, well that seems very lucky. It seems like usually we wouldn't be so lucky to have our irreducible quadratic be a derivative that we know. For example, here's another irreducible quadratic, 1 over x squared plus let's do 1 over x squared plus 2x plus 2 dx. So you can try to factor this or use the quadratic formula, but this is irreducible, I'm pretty sure. I should have checked ahead of time. So what should we do? Well, you know, really, we would like to get back to this 1 over x squared plus 1 situation, because that's when we know an antiderivative. And so if your idea is to end up with a denominator that's something squared plus a constant, hopefully that makes you think of completing the square. And if we complete the square in this denominator, we get 1 over x plus 1 squared plus 1. So however you like to work out completing the square, this is what you end up with. Quick double check. X squared plus x plus another x plus 1 plus that one. Yes, okay, that's right. And now that we have it written like this, we should do a substitution. U equals x plus 1, du equals dx again. And so this integral turns into 1 over u squared plus 1 du. And now we can use arctangent to get the integral of this. Okay. So for the final possibility, when we have the integral of 1 over an irreducible quadratic, like x squared plus 1 to a power, this, so I'm a little sheepish in telling you this, but this is actually, this possibility we are not going to find an integral for in general. And the reason is things get really messy, but fortunately, this type of integrand doesn't really show up in practice very often, so we aren't going to worry about it too much. There is a nice way to find an antiderivative for this, but it does involve some complex numbers, and so I'd rather not get into it just at this precise moment. So this is these are the main three cases, and you can see we have antiderivatives for all of these cases. There's actually one other situation that we should talk about, because I've written all of these numerators as if they're always just 1. If they're something like 2, if I change this to a 2 right here, well, we can move the 2 out in front of the integral, and then that leaves a 1 behind in our numerator, and we can proceed as before. But if you remember, there's one situation where the numerator isn't just a constant. If you have an irreducible quadratic denominator, like x squared plus 1, the numerator, sometimes it's a constant, but also sometimes it's a constant times x. So how can we handle the situation where there's an x in the numerator? This isn't going to give us an arctangent anymore, but having that x up there actually makes things very convenient for a U-substitution. If we let u be x squared plus 1, then du is going to be 2x dx, and that means 1/2 du is x dx. And now we can do our substitution. The x and dx here together make 1/2 du, and 1 over x squared plus 1 is now 1 over u, and then integrating this is no problem. So if you do end up with an x over an irreducible quadratic, you can still integrate. So except for that little complicated situation of an irreducible quadratic to a power, we can always integrate all of the terms that we get from a partial fractions decomposition. So this lets us integrate, in principle, any rational function at all, which is pretty nice.